Lecture problem 1. A 2.0 kilogram ball is hung at the end of a rod that is 1.5 meters long. The system balances at a point on the rod which is 0.50 meters from the end holding the mass. What is the mass of the rod? For systems at equilibrium, like this one, two conditions needs to be satisfied. Both of them are related to Newton's second law. The sum of the forces acting on the system of interest must equal to 0, and the sum of the torques acting on the system must also equal to 0. The first step is to identify the system of interest, which is the rod. Next step is to identify the forces which are acting on our system of interest. The first force is the weight of the rod itself, which acts at the center of mass of the rod. Notice that the rod has been assigned the mass m2. The next force is the tension that is holding the ball. That tension is equal to the weight of the ball because the ball is in static equilibrium. Therefore, the force can be simplified to be the weight of the ball itself. The other force is the force of the pivot, and that force is acting straight up, and I am going to call it the normal force. According to Newton's second law, the sum of the forces equals 0. There are three forces: the normal force which is acting straight up, and the two mg's are acting straight down. Breaking this equation into component, and the y component is going to have the following form. The normal force is a positive component. The two mg's are going to have negative components. As you see, this component has two unknowns, the mass m2 of the rod and the normal force. Therefore, it is impossible to solve for the mass of the rod. For that reason, we need to apply the second condition, which is the sum of the torques that acts on the system of interest need to equal 0. The sum of the torques acting on the rod equal to 0. There are three torques: the torque due to the normal force, the torque that is due to m1g, and the torque that is due to m2g. All of those need to equal 0. When we evaluate the torques, we need to decide about the axis of rotation, and the best point that can be chosen as an axis of rotation is a point where an unknown force is acting, and that unknown force usually is a force that we have no interest to solve for. Therefore, that point got to be where the normal force is acting, which is the following one. We are going to choose the torques that are going to turn the system in a counterclockwise directions to be positive torques, and the torques which are going to turn the system in a clockwise direction with respect to the axis of rotation to be negative torques. Therefore, the torque due to the normal force is 0 because the normal force is acting on the axis of rotation. Therefore, its lever arm is going to be 0. The torque due to m1g is going to be positive because it's turning the system in a counterclockwise direction, and it's equal to m1g times the lever arm. The lever arm is the shortest distance from the line of action to the axis of rotation, which is equal to 0.50 meters. The torque due to m2g is clearly turning in a clockwise direction, therefore it is a negative torque, and it's equal to m2g times the lever arm, which is the shortest distance from the line of action to the axis of rotation. Notice that m2g is acting at the center of mass of the rod. Therefore, from one end to the center of mass is 0.75. Subtracting the 0.50 from the 0.75, we obtain this distance to equal 0.25 meters, which is the lever arm for M2G. This is going to equal to 0. Notice that the gravity is a common factor, therefore is going to cancel out. Isolating the mass M2, we obtain 0.50 times M1 divided by 0.25. The mass M1 is equal to 2 kilograms. Substituting for that mass, we obtain the mass M2 to equal 4.0 kilograms.